Okay, our discussion is on stresses in beams. So forces uncouple acting on the beam cause bending, or that bending is what we call the flexural stresses. And it also may cause shearing stresses on any cross-section of the beam and deflection perpendicular to the longitudinal axis of the beam. If couples are applied to the ends of the beam and no forces act on it, the bending is said to be pure bending. If forces produce the bending is called ordinary bending. So we have here certain assumptions that in using the following formulas for flexural and shearing stresses, it is assumed that a plane section of the beam normal to its longitudinal axis prior to loading remains plane after the forces and couples have been applied, and that the beam initially is straight and of uniform cross-section, and that the moduli of elasticity in tension and compression are both or they are equal. So basically that is the assumption for using the formula for flexural and shearing stresses. So it has to be assumed that the section of the beam remains plane and normal to the longitudinal axis prior to the loading, remains plane after the forces and couples have been applied. So for flexure formula, so you have here stresses that is caused by the bending moment are known as flexural or bending stresses. So we have to consider a beam that is loaded as shown in our figure. So in our figure, we have the beam that is being loaded, and this is being identified. We have our compression, and of course, we have here our tension. So for this one, this is how a stress, that is how to illustrate how stresses are being illustrated that is caused by bending moment. And this is what we call the stresses that is caused by the bending moment is what we call flexural or bending stresses. So you have to take note that for if you consider a fiber at a distance y from the neutral axis, because of the beam's curvature, as the effect of bending moment, the fiber is stretched by an amount of CD. So if you're going to observe here, so this is the stretch portion of the fiber. It was stretched at a certain amount of CD. Since the curvature of the beam is very small, BCD and OBA are considered as similar triangles. So therefore, the strain is given by this equation, which is strain is equal to CD all over AB, or that will be equivalent to Y all over rho. So based on our figure, this is our Y and this is our rho. So that is strain is equal to CD all over AB, or that is equivalent to Y all over rho. By Hooke's law, strain is equal to stress all over E, or gamma, or stress sigma all over E, modulus of elasticity. Or you can have this relationship, sigma all over E is equal to Y all over rho, or therefore our stress is equal to Y all over rho times our E. So which means that the stress is proportional to the distance y from the neutral axis. So you have to take note that in this chapter, the notation f sub b will be used instead of sigma to denote our flexural stress. So we have here an illustration for a certain material that is in tension and in compression. So we have here the neutral axis, and you have here a fiber wherein you were able to, this is the diagram showing to us the flexural stresses. We have the flexural stress, and we have at the bottom part and in the top part, we have our maximum flexural stresses. And on the neutral axis, so this distance towards this point is our y, and this distance towards that point is our denoted by C. So we have to take note that our flexural stress is equivalent to my all over I, or our maximum flexural stress is equal to mc all over I. So m is our maximum moment. So our y we have identified a while ago. So that is a certain distance from the neutral axis towards a certain point. Then of course our c, we have also identified that one, that is to the distance from the neutral axis to the topmost of the fiber of the material. So we have that for our maximum flexural stress. And of course our I is our moment of inertia. Then we have our beam curvature, which is equivalent to 1 all over rho. So our flexural stress can also be equivalent to this expression. So in terms of modulus of elasticity and in terms of rho, so you can also express that one, that flexural stress is equal to E times C all over rho. Modulus of elasticity times the distance from the neutral axis to the topmost of the fiber over our rho. So we have to take note that rho is the radius of curvature of the beam in millimeter. Our m is the bending moment in Newton millimeter. So our F sub B is the flexural stress in megapascal. Our I is the centroidal moment of inertia in millimeters to the fourth, and our c is the distance from the neutral axis to the outermost fiber in millimeter. Then for our section modulus, based on our formula, which is mc all over I, or m all over I all over c, I all over c is the ratio that is called the section modulus and is usually denoted by S with units of cube. So the maximum bending stress can be written as, so you have here our maximum bending stress in terms of section modulus. So you have m all over S. You have your maximum moment all over the section modulus. So this form is convenient because the values of S are available in handbooks for a wide range of standard structural shapes. So we have here our first problem. A cantilever beam which has 50 mm wide by 150 mm high and 6 meters long carries a load that varies uniformly from 0 at the free end to 1000 Newton per meter at the wall. You have to compute, letter A, compute the magnitude and location of the maximum flexural stress. Letter B, determine the type and magnitude of the stress in a fiber 20 mm from the top of the beam at a section 2 meters from the free end. So let us have our first computation. So to start with our solution, so we simply have, of course, you have a cantilever beam. So length is 6 meters. This is a uniformly varying load, so 1000 Newton per meter. So we're going to section the beam. So once you cut this one, once you section, of course, this is our distance. This distance, you have here the total force acting for this uniformly varying load. That is 1/3 of x. So this portion from the cut section towards this end of the cantilever beam is our x. So that's one. We know that the centroid of the force is acting at the center at 1/3. So meaning to say that the centroid of the uniformly varying load is 1/3 from this side towards that centroid that is 1/3 of the length. So therefore, since the length is x, so this is 1/3 of x. So of course, this is 1000 Newton per meter. So this can denote this section can be denoted as y. So therefore, our moment here actually is, so our moment on the cut section, considering the left member, the left side, so that would be F times 1/3 of x. So F times the moment arm distance, which is 1/3 of x. So therefore, we're going to have here our value for y. So we can have ratio and proportion or similar triangle. So this is y all over x equal to 1,000 all over 6. So therefore, if we try to simplify, our y is 500 over 3 times x. So the force here, our F here actually is equal to the area of this cut portion of the triangular loading. So that is 1/2 of x times y. So if we try to substitute our y, which has 500 over 3 times x, so we have F is equal to 250 all over 3 x squared. So now we can have our moment. So we simply have to substitute from F times 1/3 of x. So this is our F, 250 all over 3 x squared times 1/3 of x. So therefore, m here is 250 times y x cubed. Okay, we have to identify letter A. The maximum moment occurs at the support when x is equal to 6 meters. So therefore, for this one, we have our illustration. So the beam has a dimension of 50 by 150. So from the neutral axis, our C is 75. So therefore, we're going to compute for the maximum moment. It occurs at the support. So at the support, so x here is 6 meters. From our solution a while ago, we're able to identify our m, which has 250 all over 9 x cubed. So we're going to have here substitute the value for x. So therefore, our m here is 6,000 Newton meter. Then to compute for the maximum moment, or we're going to compute for rather our flexural stress, maximum flexural stress. We have here our m c all over I. So we simply have to substitute. Our m is 6,000. Since this is in Newton meter, in meters, so convert to millimeters. So times 1,000. Our c is 75 all over. We have here 50 times 150 cube all over 12. So therefore, our maximum flexural stress is equal to 32 megapascal. For letter B, we have to compute the flexural stress at a certain section 2 meters from the free end, or that is x is equal to 2 meters, and the fiber, it was identified to be 20 mm from the top of the beam. So we have here our illustration. We have here, this is the 20 mm from the top of the beam. So therefore, from the neutral axis towards this top, this is our y, and that is now 75 minus 20, so we get 55 millimeters. So therefore, we can have now our moment, which has 250 all over 9 x cubed. We simply have to substitute. So we got here our x is 2. So we have here 2,000 all over 9 Newton meters. And we have now our flexural stress my all over I. So we simply have to substitute our m. Convert this to millimeters. So times 1,000 times our y, which has 55 all over our I, bh cubed all over 12. So b is 50, h is 150 to the third all over 12. So we got here our flexural stress is 869.1 kilopascal.